Unfortunately, unlike physics, I do not have time, nor do I have the, we'll say energy, which is a physics reference, I guess, to do an entire review video for AP Chemistry. Now, what I can do is I can finish the equilibrium portion that I was doing, and hopefully that will help you on the AP exam, considering the fact that I understand that many of you throughout the entire nation have an issue with the equilibrium unit in AP Chemistry. So we will finish equilibrium with part 3, solubility, in this video. And hopefully maybe over the summer, I will spend time finishing every unit. I'll update my website, and in the future, if you're watching this in the future, you should be able to use my website as a review tool, as well as all these videos, which I plan to finish to completion. Even though for me the AP exam is over, I will still have these videos going out for everyone in the future. So let's finish this. So here we have an example of a solubility question. Magnesium hydroxide is in equilibrium with the ions magnesium and hydroxide, and it's KSP, which is its solubility point, point or product at equilibrium. Solubility product, we'll say, is the best definition. At equilibrium, hence why it's K, is 1.0, which is 2 sig figs, times 10 to the negative 11. Now, what does this mean? It means that it is very unlikely to dissolve in water when it's a solid. So say you put solid magnesium hydroxide in water, it's very unlikely to dissociate in the water because its solubility product is so small. 1 times 10 to the negative 11 is very small. And as we remember from earlier in the equilibrium unit, that a higher K value means it is more likely to dissociate or for the reaction to occur. So this is essentially just the net ionic because the water is like on this side and on this side, so it doesn't really matter. This is really just a dissociation equilibrium. However, it goes from here to here because it's dynamic equilibrium. It doesn't just dissociate and then stay dissociated. It dissociates until it reaches equilibrium, and then it dissociates at the same rate as it goes in the reverse reaction. So what we're going to do first is we're going to find what is known as the molar solubility, which is represented normally by the symbol S and is normally in units of molarity. So the molar solubility is the solubility of 1 mole of this to dissociate in water. And how do we calculate it? Well, we'll do a sort of equation. So say that the concentration of Mg2 plus and OH minus, which is squared because there's 2 of them, right? So this is our K. And our K is our K solubility product. So this is equal to 1.0 times 10 to the negative 11. Now say that the concentrations here are in terms of X. Say that, or instead of X, why don't we say S? So this is S. Molar solubility meaning how many moles will actually dissociate. How many moles of this will actually dissociate? So say that the concentration here, I don't know why I erased that, but is S, right? So I'm going to write it a little bit higher so I can do this. So say that that is S, okay? And because this and that have the same coefficient, this is also S, but this is 2 of that. So this is actually 2S. So we can change these concentrations to say S times 2S squared is equal to 1.0 times 10 to the negative 11. Okay? So we expand this and we get 4s cubed. So 4s cubed is equal to 1 times 10 to the negative 11. We divide by 4, and we get 0.25 times 10 to the negative 11, which is 2.5 times 10 to the negative 10. So we get 2.5 times 10 to the negative 10 is equal to s cubed. Now we just need to find s. So s is equal to the cube root of 2.5 times 10 to the negative 10. So the cube root of 2.5 times 10 to the negative 10 is, well, I'm not exactly sure since I'm not using a calculator. So we'll say that it is just the cube root of 2.5 times 10 to the negative 10 molar. And that is our molar solubility for this question. Now, the next question that we will do will still involve the solubility point, but in this case, we are going to be given the number of moles of reactant, the amount of moles of the solute. So it's going to be the same reaction of magnesium hydroxide okay? However, the difference is the fact that, say that we don't know the KSP, because I just made up a random KSP. Say that we don't know the KSP, okay? But say instead that we are given the moles of, not the moles, well, say we're given the moles or the molarity, or why don't we just say that we're given the concentration? Well, not really concentration since it's a solid, so why don't we say that we're given the grams instead? So first, let's say we know the molar mass of magnesium hydroxide is about 26, I want to say, plus 2 times 17, so it's 34 plus 26. That's about 50? No, 60. 60 grams per mole. So why don't we say that we have 360 grams of MgOH2, of magnesium hydroxide. So if we have 360 grams of magnesium hydroxide, then how many moles do we have? Well, we have 6 moles. And say that this is actually in a solution of 1 liter, so this is really 6 molar, but this is a solid, so we don't really consider it molar because it's not an actual solution, it's solid. So this is 6 moles of magnesium hydroxide. So say we're given 6 moles of magnesium hydroxide. Well, this is not 6 moles of magnesium. Why? Because the KSP value is a lot smaller. So if we're given 6 moles of magnesium hydroxide, and we know that the K value for these is small, right? Say we're actually given the KSP is 1.0 times 10 to the negative 11. Before we were imagining that we didn't know it, but now let's say that we do know the solubility point at equilibrium is 1.0 times 10 to the negative 11. Now, what we can do is we know that this is 6 moles. So what we'll do is we will do a ICE table. So we have our I, our C, and our E. And here we have MgOH2, magnesium ion, and hydroxide ion. So we know that we're starting off with 6 moles. So we're going to have to deal with moles instead of molarity, but say that our volume is just 1 liter. Say our volume is just 1 liter, right? So it doesn't really affect anything. So 6 mole, And then our change is minus x, which we know is probably going to be our molar solubility in terms of the 6 moles. And our equilibrium concentration, or in this case will be our equilibrium moles, will be 6 minus x moles. And magnesium, the magnesium ion, well, it starts off at 0, and this one also starts off at 0. The change is going to be plus x, and this one's going to be plus 2x because there's 2 hydroxide. And this is going to end up being x, and this is going to be 2x. Okay, so we know that this is equal to our KSP value. So we'll just do that over here. We'll just make some room. Okay, so products over reactants. So x times 2x squared, because there's 2 of them, over 6 minus x is equal to 1.0 times 10 to the negative 11. Now in this case we're trying to find the, why don't we go ahead and try and find the pOH. So our goal is to find the pOH of this solution. Now normally we would consider this a strong base, but this is not a strong base. Why? Because it doesn't dissociate well in water. It is in fact actually a strong base, but not in water. It might be a strong base in a solution that is not, in which the solvent is not water, but something that allows the solubility point of magnesium hydroxide to be larger. So here is this, and so because this is so small, we can just imagine that the x on the bottom doesn't really matter, and we'll just multiply it by 6. So we end up with 4x squared times x, which is x cubed, is equal to 6 times 10 to the negative 11. Now we divide by 4, and we're left with x cubed is equal to 6 over 4, which is 3 over 2, so that's 1.5 times 10 to the negative 11. So then x is equal to the cube root of 1.5 times 10 to the negative 11. So the concentration of hydroxide is 2 times x. So that's going to be, we'll erase this volume because we already know that the volume is 1 liter. So that means that 2x, which is equal to the concentration of hydroxide, is equal to 2 times this, which is going to be the cube root of 8 times 1.5, which is going to be 8 plus 4, which is 12. So that's going to be 1.2 times 10 to the negative 10. And that would be the cube root of that. So that is the concentration of that. So then we need to find the pOH, and then why don't we find the pH as well, just for kicks. So the pOH is going to be the negative log of the concentration of hydroxide, which is going to be equal to the negative log of 1.2 times 10 to the negative 10 to the power of 1/3, which is going to be equal to negative 1/3 times log 1.2 times 10 to the negative 10, which is going to be around 10 times 1/3. And it's going to be a little bit less than 10, so it's probably going to be around 9. So 9, why don't we just say 10 just to be certain, because I know it's going to be around 10. It's a little less than 10, but let's go with it. Times 1/3, which is going to be about 3.3333. So why don't we just say that it's going to be 3.3. So this is approximately, we'll do the symbol for approximately, 3.3, and that's the pOH. So the pH would be 14 minus 3.3, which is equal to 10.7. So we'll say that that is the pH of this. And it's not exactly the pH, but it's close enough to the point where we can say that it is the pH of the solution, 10.7. Now, finally, why don't we get into more of the conceptual idea instead of doing the math behind it. Now, what would happen if we were to increase the pH of the solution? Well, if we were to increase the pH of the solution, that would mean that we're adding more protons, which would probably mean that these protons or hydronium would react with this to form water, so this concentration would decrease. And if the concentration of hydroxide decreases, then the equilibrium, due to Le Chatelier's principle, will shift in this direction, the direction of the products, meaning that the solubility will actually increase because more is being dissolved. Now, if we were to add magnesium nitrate to the solution, what would happen is that the concentration of magnesium would increase, and so the reaction would shift in the opposite direction due to Le Chatelier's principle, and so we would actually form more of the solute, which would mean that the solubility actually decreases when you add. So if you increase the concentration of the products by any means, you're going to shift the reaction in the direction of the reactants, which would mean that you are actually decreasing the solubility. But if you decrease the concentration of this, or you increase the concentration of that, then you're actually shifting the reaction in the direction of the products, which would mean that your Q is less than your K, which would mean that it's going to form more products, which would mean that it's more soluble. So that means that more solute means more soluble, which kind of makes more sense because it's going to want to make more in order to reach that equilibrium. And if you decrease this, it's going to want to make more to reinstate equilibrium because Q is going to be less than K. But if Q is greater than K, your solubility is going to decrease. And so that's it for this video on equilibrium. And finally, we finished our equilibrium unit. And hopefully you will do well on your AP exam, which for me is tomorrow.